Okay, so today we are going to be looking at chapter 3.3, or molecular shapes and dipoles, where we're going to focus on something called the valence shell electron pair repulsion theory. Now, we have V.S.E.P.R underlined because we normally shorthand this to the V.S.E.P.R theory. Now, this is used to predict the three-dimensional shapes of molecules, so we have to kind of think in 3D space. And this is based off of electrostatic interactions of the electron pairs. So both bonding and non-bonding. So we will need to pay attention to how everything looks and how they interact. So how this works is that the V.S.E.P.R theory is based on the fact that molecules are going to arrange themselves around the central atom so that the peripheral atoms are as far apart as possible. Now, for molecules that have lone pairs, these tend to repel the peripheral atoms and they're going to affect the shape. So we're going to notice that when we talk about bond angles and everything like that. So just a little reminder on some of our terminology. We have bonding pairs are the electrons shared by atoms in covalent bonds, and our lone pairs or our non-bonding pairs are not involved in bonding. So this three-dimensional shape that we're going to be looking at, the technical term for it is called stereochemistry. And what this is a study of our three-dimensional spatial configuration of molecules and how this arrangement affects the shape and the chemistry. Shape with an S, not with a C. So one of the main applications of stereochemistry, and you can kind of read down here, is enzymes in our body. And that is that enzymes, they kind of, if you learn this in bio or if you're studying in bio, what they have is this sort, it's called a lock and key mechanism, where if you think about a key, only a specific shape can open up a lock. So for specific reactions in enzymes, they're only going to react with certain molecules, and it's based on the shape. So what we have right here, there's about 3,000 different enzymes in an average living cell, and each one carries out or catalyzes specific reactions. Now, you don't need to worry about those numbers, but this is just where the three-dimensional shape will hold or will affect the molecule. And wrong stereochemistry or wrong stereoisomers are called, then reactions won't occur. So that's why it's important in this kind of little idea on what we have, the lock and key analogy, right? Everything needs to match up perfectly. Now, molecular structures are three-dimensional and therefore need to be represented using our V.S.E.P.R formula. So valence shell electron pair repulsion formula. To represent 3D shapes on paper, we need to use the following conventions. Now, of course, in order to think in three-dimensional space, it's kind of like when you draw a cube, right? This is a square. In order to draw a cube, we extend the axis out, and we kind of imagine that there's more going on than what's there, right? So just think about that when we need to be able to figure out how to give depth or give three-dimensional shape to something that we're writing on 2D paper. So when we see something like a solid line, I'm just going to erase this cube. When we see a solid line, this means that the bonds are on the same plane as the paper. So a solid line is just going to look like that. So that means if the molecule is lying down on the table, it is going to be completely parallel with the paper. Now, you are going to see wedges, and they're going to look like this. Whenever you see a wedge, we're going to assume that the bond is out of the plane of the paper, meaning that if you're looking down at your paper, that bond is coming up towards you. And if you see a dotted line like this, that means that the bond is going into the plane of the paper, or just imagine your paper is flat on the table, so that means it's going in towards the table away from you. And these are the connections, or these are the conventions that we're going to use for drawing our 3D shapes. So for example, methane, which we're going to get into why it has this alone, but I chose this molecule just to kind of show you on how we have two bonds here that are on the same plane as the paper, right? So on the same plane as the paper, this bond right here is coming out, And that one there is going into, coming out of the paper, and that one is going into the paper. So that is kind of just an example on the conventions that we're going to use. Now we're going to look at 5 shapes, and only 3, is it 3? No, 2 of those shapes are going to use the dotted or the wedged lines. So as we're going through, you will need to do a little bit of memorization on which ones will be which and when they apply. All right, so we're actually going to go through right now all of the shapes. So the 5 main shapes that we're going to be looking at and how to draw them. And of course, we're going to be looking at the bond pairs and the lone pairs to figure out which ones are going to be which. So let's look at how to figure these out. So our steps for predicting molecular shapes. First, we need to draw the Lewis or the structural diagrams. Now that's what we've been working on Thursday, Friday of our classes, right? And of course, we have our video lessons put up on molecular compounds. So we will need to look at the Lewis and structural diagrams first. Next, we need to determine the total number of bonding electrons around the central atom. So just a little heads up is that a double or a triple bond is counted as one electron group. Okay, meaning that if we had a molecule like HCN, this triple bond right here, this is counted as one E negative group, bonding group, and this is also one electron group. So for hydrogen cyanide, we have a grand total of 2 electron groups total. All right, so this will make a little more sense when we get to the lone pairs and the bonding pairs type thing. Now, after we draw out the shape, we're going to determine the total number of electron groupings around the central atom, and that's what I just did right there. So we draw out the shape, and then we look at our electron groups. And we're also going to look at the total number of lone pairs around the central atom. So in this example right here, carbon has no lone pairs. And based on the combination of lone pairs and bonding pairs, or electron groups, that is going to determine the shape that we draw. So let's look at the shapes, let's look at the combinations, and how we need to draw these. So our first shape is something called tetrahedral. Now for these molecules, the central atom is going to have 0 lone pairs. Okay? So really, when you look at, 2 examples right here, we have a carbon base and a silicon base. So for our nonmetals, these are our only options really, because nitrogen has 1 lone pair, oxygen has 2. Fluorine, chlorine, bromine, iodine has 3. So really only carbon and silicon could do this. But we also need 4 bonding pairs, so no double bonds, no triple bonds. Now for example, methane, CH4. Now how we would draw methane, carbon's in the central. We're going to have 1 hydrogen on the plane of the paper, another hydrogen on the plane of the paper, 1 hydrogen wedged, and the last molecule dotted line going back like this. So that is going to represent how our carbon would bond. Now I know I didn't draw the Lewis formula and stuff like that, but we're just looking at, once you figure out these here, that's what we're going to go for. Now even our silicon tetrachloride as well. Now if we did this one out, silicon tetrachloride, we have 1 silicon and 4 chlorines. We know silicon has no lone pairs and it's going to have 4 bonding pairs because of the tetrachloride. All right. So how we're going to draw this is the exact same thing. We're only changing out our elements. So instead of carbon as our central, we have silicon. Now instead of hydrogens going around our central atom, we have chlorines. And tetra, so there's going to be 4. So we got 2 on the bond, 2 on the plane of the paper, so that's our straight lines. We have 1 that's going to be coming out of the plane of paper, and then 1 going behind using our dotted line. Oops, sorry, not S, that needs to be Cl. Just like that. So you'll notice how they have the exact same shape, how they're drawn out. The only difference is our elements. So these here, we're always going to see the shape, or you should always represent this shape if we have something, the central atom has 0 lone pairs and 4 bonding pairs. Now, just a few other little things here. The description, we have a central atom having 4 bonding pairs, but the bond angle for all these here is a perfect tetrahedron. So if you actually Google that, what that needs to be, and if you did the geometry in math, I don't know if you touched 3D shapes, but anyway, the bond angles, or the angles on a perfect tetrahedron, is 109.5 degrees, because there's nothing repelling it. There's no lone pairs repelling. Now our next one. Oh, sorry. Almost forgot about that a little bit. Just a little explanation of what a bond angle is. So a bond angle is just an angle formed by all bonds around a central atom. So a lone pair, we're shorthanded LP, so a lone pair of electrons forms a strong repulsive force that tends to repel or affect. Sorry, those are ugly looking F's there. I'll try this again. It affects all the bond angles more than the bonding pairs. So as we start adding lone pairs, we're going to see the bond angles start changing. All right, next slide. So our next geometry, and this is the last one that uses the wedge and the dashed lines. All the other ones after this are only going to use straight lines. So we have our trigonal pyramidal. So please remember these names as well. Now, if you want to, you can just say pyramidal. You don't need to write out the trigonal, but either way, this is the important one, so you can record it as pyramidal or trigonal pyramidal. Now, the combination of these here, we're going to have 1 lone pair, and we're going to have 3 bonding pairs. So, for example, the only atoms that have 1 lone pair is nitrogen and phosphorus. So that's why my 2 examples right here, I have ammonia, which is NH3, and we have phosphorus triiodide. Now, how our trigonal pyramidal compounds look, we're going to have our central atom, in this case here, nitrogen, with the lone pair. Now we're going to have 1 bond on the plane of the paper. We're going to have 1 bond coming out of the plane of the paper, and 1 bond going into the plane of the paper. And all trigonal pyramidals should be represented like this, where we have 1 bond on the plane, 1 coming out, 1 going in. And our phosphorus triiodide, well, it's going to have the exact same shape. The only difference is that our central atom is different and our peripherals are different. So our central atom now is phosphorus, it has a lone pair. We're going to have 1 iodine on the plane of the paper. We're going to have another iodine coming out, represented by a wedge. And the last one going in, also represented by a dotted line. And that will be our phosphorus triiodide. Now, I know it's kind of difficult right now to imagine these 3-dimensional shapes. So right now we're going to get the theory out of the way with drawing them. And then at a later date, so Wednesday after the quiz on Tuesday, we are going to be doing a lab where we actually get to use models that have these shapes. Now, where these here have a lone pair on top, it's going to affect the bond angle. And when we look at these here, the bond angle is less due to the lone pair. So the bond angles for these here is not a perfect tetrahedron anymore. It's about 107 degrees. Now our next shape is our bent or our V-shaped. So that just means that you can use any of those terms, either bent or V-shaped. They both mean the same. So these here have 2 lone pairs and 2 bonding pairs. So of course, when we look at atoms on our periodic table that has 2 lone pairs, we have oxygen and sulfur. So that means most oxygen and sulfur molecules will form a V-shaped. So water we know is H2O, and sulfur difluoride, we can get that. So how these are represented on paper, we need to make sure that we actually show a bent or a V-shaped. So in this case right here, draw it like a V, where we're going to have hydrogen going down. We have our oxygen molecule here, and completing the V looks like that, right? So we have our oxygen molecule, looks like a V, that's why it is V-shaped, and our 2 hydrogens. And same thing with our sulfur difluoride. You can have your V upside down as well, so I'm just going to draw it differently for you guys. You can have your sulfur looking like this. You can have the bonds going down as well. Difluoride, it's going to look like that, and difluoride will look like that. So either way, you can draw it like water or like this. It doesn't really matter if the bonds are going up or going down. I just like to draw them going up because it looks like the V shaped, right? This is kind of a reverse V, but still, you can still see it is that shape. So just make sure when you're doing these here that you do not do line or dashed or wedges. It's only straight lines. Now our next one is something called trigonal planar. Now, same thing with our trigonal pyramidal, we said we can get rid of that word trigonal. Well, same thing with this one. If you don't like the word trigonal, just remember the word planar. Now, this one gets its name because planar means that it's going to be on the plane of the paper, meaning that we can just use straight lines. So these here have a combination of 0 lone pairs, but we have 3 bonding pairs. So boron is a unique one where it is kind of a non-metal, but it will form trigonal planar compounds always. But also we're going to notice carbon-based molecules and silicon-based molecules can form these as well because they don't have lone pairs. So for our boron trifluoride, a trigonal planar, we have the molecule or the central atoms in the middle. You're going to have all 3 bonds on the plane of the paper, but try to get the bond angles proper. So basically you need to have all 3 bonds equally spaced apart or equal angles, which is 120 degrees between each one. So it needs to look like that. Okay, I am going to be very picky about bond angles. Like, I don't expect you to get a protractor, but they need to be very similar to what I have drawn here. Now for our formaldehyde, CH2O, this one is still going to have 3 bonding pairs, but just remember that double bonds and triple bonds count as 1 bonding pair. So our formaldehyde will look like this. Carbon's in the middle. This double bond, remember, counts as only 1 bonding pair. So that's 1 bonding, hydrogen, hydrogen, boom. We have our trigonal planar formaldehyde, right, with 1, 2, 3. So that's why we had that note up there, and I pointed out that if you see a double or a triple bond, it's 1 bonding pair. And that is it. All right. With this, we only have one more group left, or one more shape. And with that one, that is our linear shape. So with this one here, the combination that we're going to see, 0 lone pairs and 2 bonding pairs. Meaning that, well, we need atoms that have no lone pairs, first of all, as a central atom. So that means carbon and silicon are going to be key candidates for this molecule. And that's why we're having carbon dioxide and hydrogen cyanide. Because cyanide, remember, is CN, meaning that there's carbon as a central atom as well. So first of all, our carbon dioxide. How this is going to look, carbon is a central atom. Now there's no lone pairs, but in order to get our 2 oxygens, we're going to have a double bond oxygen on one side and a double bond oxygen on the other side. Boom, that is carbon dioxide. And notice how I drew everything in a straight line. That's because it is linear, right? So do not draw them like V-shaped. Draw them linear, right? That name means linear, draw in a straight line. For our hydrogen cyanide, it will look like this. HCN, where we have carbon and nitrogen is undergoing a triple bond, so that is still only 1 bonding pair, and this one right here is the second. So it's still 0 lone pairs, 2 bonding all around the central atom. Now, I know the peripherals have lone pairs, but they are not going to affect the shape. It's only around the central atom. That is it. And of course, the bond angles here, we have 180 degrees. Now, I'm not going to get you guys to memorize all the bond angles, but those are just there to kind of give you an idea on when we've seen the lone pairs, they're affecting the bond angles greatly. And when we don't have lone pairs, everything is spaced out as evenly as possible. Now, for the remainder of your time working on this, you guys are going to practice this. And like I said, we will end up going over a lot of this later. I have the answer keys up to this, and of course, make sure to do your CYU once you get the work done that we're going to do down below here. So on the next page, we have all this. Now, I'm going to go over oxygen difluoride with you, just so you know exactly where to put everything, all right? So first of all, I know it says lone pairs and bonding pairs up here. Now, some of the ones, when you get really good, you can just read the name and be able to know. Now, if you're not at that level, that's fine. What we're going to do is do Lewis, then structural formula. So for oxygen difluoride, now I know we don't have spaces here to figure out the central atom, but if you need to do it up on the top right here, you can do your oxygen, and we know fluorine will look like this, right? We can tell fluorine has 1 bonding electron, oxygen has 2. So because it has 2, I know this is my central. And if it's my central atom, I know already the number of lone pairs are going to be 2, but I'll get to that now in a second. So the Lewis formula, I start by writing my central atom in the middle, and I do this. I draw it like that. Now I put in each of my peripherals, and I create 1 bond. I put in my other one, same thing, I create 1 bond. Now from here I can go straight down to structural formula. Just make it look a little neater. Like this. Alright, so once you get the Lewis and structural formulas done, that's now when you look at the central atom. Now, once again, I know it's oxygen. So when I look at oxygen from my structural formula, I can tell that there's 1, 2 lone pairs. And when we look at our bonding, we see 1, 2 bonding. So we have a combination of 2 and 2. That shape, I'm going to write down here, is V-shaped. Now, you can refer back to your notes if you want to, but it should be a V-shaped. So therefore, our structural formula is going to be shaped like a V, where we go F, V, O, F. Put in my lone pairs, and we are done. So that is kind of how you fill these out, right? Now, once again, if you know exactly, once you figure out your central atom and you get really good at, like, you can potentially start right up here with figuring out the lone pairs and the bonding pairs, right? But you should be going Lewis formula, structural formula, then start figuring stuff out, all right? So for what we have right now with the remainder of the class, or the remainder of your time if you're watching this at home, what you can do is finish off the rest here. So the boron triiodide, we have silicon disulfide, CH3I, that one's called iodomethane, but that's why I don't have the name there. And we have a few on the other side as well, so nitrogen trifluoride and SiH4. And then you can then look at this right here. So sometimes you get molecules with more than 1 central atom. All right. Now with these here, if you look at it, if you draw them out, and we've already worked on drawing larger molecules as well, but if you know there's more central atoms, you can draw them out and then figure out each one, right? So carbon is going to be tetrahedral here, and oxygen is V-shaped. Now these here are going to be a little more challenging to do. So if you just want to work on these here, so the small ones first, open up your CYU book and do the smaller ones, that's fine. If you want to start tackling the bigger ones, please do, right? Where now we have the number of spaces here are for how many central atoms are there. So for ethene, we should have 2 central atoms, right? For dimethyl ether, there's 1, 2, 3 spots, so there should be 3 spaces or 3 central atoms, right? So these here are definitely a little bigger, a little more challenging. So if you do want to jump ahead, please do go ahead and do it. If not, we're going to tackle some of these bigger ones when we come back later this week before we get on to molecular polarity and dipole theory. All right, so finish off these here inside the book. Do your CYU, and if you really want to challenge yourself, see if you can find the bigger molecules. Check your answer keys on Google Classroom, And if you want to replay, for those of you who are watching this in class, I think I have the Chromebooks booked out as well. So if you want to grab a Chromebook and replay this at your leisure, if you're just unsure of some of the stuff or you never had a chance to fill everything out, just grab a Chromebook and replay this. And of course, if you're at home, you have the ability to do it anyway. All right, so that is it for today. I'll see you guys later, and we're going to come back to go over those bigger ones and look at our next section, which is dipole theory. All right, see you later.